there's a tendency to think if we have better observations, then we automatically know how to use our models. But our models are different to reality. Mm-hmm. Better observations of reality are really good, but they don't necessarily translating them into how we use our models is a really interesting and problematic issue.
Welcome to London's Royal Courts of Justice. Whoever said it always rains in London? Quite the opposite. It's an absolutely beautiful winter spring day. I'm not going to the Royal Courts of Justice. I'm going here to the London School of Economics. And I'm over there to meet a guy called David Stainforth. Absolutely no relation to me. I'm called Stainforth. He's got an extra I in his name, Stainforth. David's been kind enough to agree to meet with us today. He's just written a book about predicting our climate future. What we know, what we don't know, and what we cannot know. It's a really, really fantastic book if you want to go deep in understanding what's really going on in our world, instead of listening to people that just claim things without knowing the facts. We've come to find out what the real facts are. David's found some time for us. We really appreciate this, and I do hope you enjoy our conversation. Professor David Stainforth, thank you so much for finding the time spontaneously for us today. I called you up this week, said we've almost got the same name, so there must be something in the stars for us there. Thank you for finding the time, and thank you as well for writing this amazing book. But it's really fantastic. But to start off with, welcome.
Thank you. Thank you so much for getting in touch. Thank you so much for enjoying the book, although I gather you've still got some of it still to read. But it's been great chatting to you this afternoon so far.
Yeah.
It'd be really nice to talk to you now.
Yeah. No, we just had a chat and basically we both agreed, let's just film this and create a podcast out of it, because it seems like we're talking about very similar things. We're singing from the same hymn sheet, as you would say.
Absolutely.
The book, of course, we should definitely tell people what it's called. Here it is. Unfortunately, because I wasn't planning on doing this, then I haven't actually got the cover with me, but it is Predicting Our Climate Future, What We Know, What We Don't Know, and What We Will Not Know, or What We Cannot Know.
What we can't know.
What
Yes.
we can't know. Yes.
Absolutely. That's exactly what we know, what we don't know, and what we can't know. Yes.
Could you tell the audience, could you tell the listeners what that means exactly?
Okay. So it's about what we understand about climate change and how... well, I guess his starting point is saying the way we talk about climate change, we need to see it as a prediction problem, because we know something about the future if we achieve net zero by 2070 or something, and we know something about what the future will look like if we don't. And that's what gives us a choice about climate change. So the problem then is what do we know about the future? How do we know it? What's reliable and what's not reliable? And I argue that there's some things about climate change and about the future under climate change, which are just really reliable. It's sort of basic physics. It's kind of school level physics. It's not really open to debate. It's just stuff we know. But there's a whole load of other stuff that we don't know half so well. And I guess one of my frustrations is that in the media, these things get mixed up, and that leads to confusing conversations. Because is that known, or is it just speculated? Because some things we know and some things we don't know, and that leads to issues, all sorts of really interesting physicsy, mathsy issues about chaos and non-linearity, which say actually there's some things that we just can't know.
So let's focus on the things that we do know, because I think that will also help us to understand why it's something we should care about. Now, it might sound a bit ridiculous to say, why should anyone care about climate change? But there are actually debates going on about that. But let's talk about the hard facts to start off with, because I think it's wonderful to see a scientist like yourself, a fellow physicist. I started our introduction today. You said, so who are you? I said, I studied physics, but I wasn't very good. You obviously were, so well done. And I'm so happy you're doing that. But it's great to see a scientist who's actually saying, well, we don't know everything. But what do we know? I remember there was part of the book, and it talks about, for instance, where water's going to be distributed throughout the world and how it's going to impact infrastructure. How should we prepare for that? What's happening there?
Oh, okay. So I tend to express it as the confidence we have, what we know about the existence of the threat of climate change is really confidently known. And what I mean by that is increasing mankind's emissions of greenhouse gases leads to increase in carbon dioxide and nitrous oxide and other gases in the atmosphere. That's going to trap heat. in the lower atmosphere where we live, and in the upper oceans, and that means we're going to get warming. So it's very confidently known that human emissions of greenhouse gases has led to warming and will continue to lead to more warming. And then there are a number of other physical things that we know about that. We know that a warmer atmosphere will lead to increasing water vapour in the atmosphere. A warmer atmosphere can hold more water vapour. That leads to even more warming. And it also leads to more energy in the atmosphere. So you'd expect more extreme events. So you expect these sort of extreme events that we see, whether that be floods or droughts, these sorts of extremes, or tornadoes, these sort of things. You would expect an increase in these sorts of events because there's more energy in the atmosphere. So we know about that. Where it gets a little bit more difficult is why that matters. So there's two areas I could go here. One is into these areas that we don't know so well. Is okay. I say we might have more extreme events. We'll have warming. Yeah. You'll also have an intensified hydrological cycle, but unfortunately that's problematic. It's an intensified hydrological cycle, which means you would expect more rain, essentially, across the planet.
Okay.
Unfortunately, that doesn't mean everywhere gets wetter.
Right. Okay.
Some places will get drier.
Everyone's going to have a humid day, or everyone's going to have a thunderstorm.
No.
Okay.
No.
All
some
right.
places will get wetter. Some places will get drier. Some places will get wetter through more drizzle, as it were, more normal.
So just light rain.
Yeah.
I'm not sure if drizzle's an international word.
Oh, is it not?
I don't know. I've got no idea, to be honest.
It definitely should be. It's a great British word.
Yes. Light rain, folks. Maybe it's international.
I think there must be some Scottish versions of it as well.
Yeah.
Anyway, but other places will see this rainfall come in extreme events, so you'll get particularly heavy events.
Yeah.
So you might end up with summers in some places being generally drier, so your soil and your ground is drier, but still getting more extreme events. And this is really bad because then you've got intense rainfall over dry ground, leads to runoff, which is quicker, and increasing floods and these sorts of things.
Right.
And our problem is it's really difficult to say where we'll get wetter, where we'll get dry. You can say it in some places, but not in others. So you can say some things, and now you're already getting me to talk about, we know a bit about this, but we don't know about that.
Well, we're going to move on to that in a minute. But I had another fascinating conversation, actually, with the lady who gave me this book. I'm not going to big her up because I don't know if she wants to be mentioned, but it's somebody I've known for many, many years, and she actually works in the insurance industry, and she models basically the future of climate. She knows all about what you're talking about what you can and what you cannot know. But it's fascinating to hear things like, for instance, we're insuring new technologies, like, for instance, hydrogen capture or big solar farms, large wind areas. And it's a new technology, so you don't know what's going to go wrong. You know, how long does a hydrogen capture technology work for? If I think about a town close to where I live, they used underground energy to warm the town and to create electricity, and then unfortunately they had a chalk layer and the whole thing went up. So it was a beautiful, beautiful medieval town with old sort of Black Forest style German wooden houses, and a lot of them it's like, half a metre higher for one half of the house than the other half of the house. Been quite a big thing. So that's the one side, is it's new technology, we don't know what it does. The other side is how big are the hailstorms? And so, if I think about it, if we look at what's happened recently, unfortunately, in Valencia, I mean, we have a client and they have a place in Valencia, and they were saying, half the town was devastated, the other half of the town, 10 miles further on, didn't know anything about it. It was a very local storm. And I mean, what should a town like Valencia be doing now? Can they protect themselves for the future?
So that is a really good question. I'm not sure it's amenable to a quick answer.
Okay. Well, we got time.
Yes. So I think, that it's a really good question because it illustrates the difficulty of the problem. So I don't know the details of Valencia, but I completely recognise the situation where one part of a town gets completely devastated and another part just doesn't recognise that anything has happened at all. And this is the kind of problem that we have.
Yeah.
Because when you're building infrastructure, if you're building bridges or roads or new houses, and across Europe and America, there's a need for new housing. So you're putting up housing, you're putting up buildings. How do you know how to make them resilient? How do you know how to adapt what you have so that it's going to be sustainable for 100 years or more? And your problem is you don't know if the other half of Valencia is going to get hit, or whether it's somewhere else down the coast, some other village, some other town. You don't know. We don't know those sorts of levels of predictions. But what you do know is these things are going to come along more frequently.
Right.
So what you need to do is adapt your planning systems to be generally more resilient,
Right.
to be more prepared.
Okay.
And not just individually, not just individual towns, but the whole infrastructure. What you don't want is for your whole county. I'm trying to think of what the regions in Spain are called.
I was going to say canton, but that's Switzerland.
Yeah,
Anyway,
that's right. Yes, you don't want the whole region to be vulnerable in the same way.
Right.
And there's a danger there, because we look to models and we look to science to tell us what things will change. And then we push that out to builders, engineers, planners. And there's a risk there that your canton in Switzerland might all use the same information. Now, the danger there is if that information is wrong or misleading in some way, the whole of your region is now vulnerable.
Right.
So you want diversity in response. You want flexibility.
Okay.
Yeah, I could say more about flexibility. That's sort of... come on.
No, you're all right. Don't worry. I don't want to...
And just sort of thinking about that flooding protection. One of our problems is, because we don't know quite what's going to happen, you could build to what we think is the worst case.
Okay.
And you might argue that's a good idea.
That's sort of what we did in the past, right?
Yes, but we've got a really wide range of worst cases now. Can we afford to do that? In some places we can, sometimes we can't. It could be overkill. On the other hand, what you can do is build with flexibility in mind.
Okay.
So you can sort of say, this we really care about. You build for the worst case. But many other places you might say, well, okay, we build, say, flood protection measures, but we build it in a way that says we'll build to what we think might happen, but we build it in such a way that we can extend it in the future as things seem to be developing and we learn more.
I see. So a kind of a modular approach.
Yeah.
That's interesting, because I mean, we're here at the LSE, London School of Economics. Hey, I feel like I studied here. I feel so important being here, you know. We're here at the LSE. I think it's absolutely fantastic that the School of Economics has invited a physicist like yourself for 15 years to join this debate. It's important because it is an economic debate. We're not talking here about doing something philosophical. We're talking about something that's going to cost the world a lot of money, and also something that there are many opportunities to earn a lot of money as well. But if I think about London, I believe it was Margaret Thatcher. I think I was a kid or a teenager at the time, and there's the Thames Barrier. That's a flood barrier, right?
Yeah.
And I don't think Margaret Thatcher built that because she likes architecture. I think she bought it. She wanted to protect the financial district of London. Is that a fair assumption?
I believe so. Yes. I don't know the details, but yes, I believe so.
If we think now, that was probably 40 years ago that thing got built, 50 years ago that it got planned and signed off or something. But you know, it's lasted this long. Can we plan with things like that in the future as well? How far do we know? How far into the future can we look? You know, how big is your crystal ball?
So the Thames Barrier is a really good example here.
Okay.
How far can you look? I think we can look quite a long way, 50, 100 years.
Right.
This is something we can look.
Yeah.
And we will have information about that. But, and this is kind of what my book's about, it's sort of, we will have information, but it's not necessarily as precise as you might want it. Increasingly, we need to talk about probabilities, only we're not even precise about the probabilities either. So it gets mucky, but none of that is to say we don't have information. We do have information, useful information about what climate change will look like under different scenarios. The challenge is to embed that information in good decision making. And that's not an easy thing to do. And decision makers tend to look for more certainty than we can provide. So there's a need to be honest about the uncertainties, and there's a need for decision makers to develop systems that can build in the character of uncertainty that we have. And there's lots of really groovy and interesting ways of doing that. And decision making under deep uncertainty is a theme in itself. Maybe we'll come back to that in a moment. But can I go back to the Thames barrier?
Oh, please do. Please do. You can
really
go anywhere you want. This is your platform.
So,
I know you do a lot of public speaking, but we're just so happy you found time for Progress Factors.
So you're right. The Thames barrier is built to protect the City of London. And it was anticipated to last to be robust for quite a long time. I don't know quite how long time, but longer than is the case.
Like 100 years.
I believe it's that sort of order. It is now assessed to be not. It is not thought that it will be sufficient for the next 100 years. And indeed, they've already. I can't remember the statistics, but there are statistics on this. It is being used far more often than it was planned for. And I can't remember what the numbers were.
Being used basically means it closes the gates.
It closes the gates.
Right. So that's an interesting
in a way
KPI. We talk about key results, and KPI is basically how often do the gates close is a good prediction.
And it was expected to be, and I can't remember, maybe once a year or once every 2 years or something. And I don't know the numbers, but it's being used multiple times every year.
Right.
And this was not what was planned. And I believe it's also been used in a sort of overprotection way. There's a sort of basic protection, and then there's a sort of extra level.
Oh, I see. It's the turbo protection thing.
But I don't know the sort of details about that. But it is something that has been studied. Colleagues of mine in the Met Office and elsewhere have studied this. And it's been an active thing where they're saying, OK, what do we do? Because we don't think it's going to protect us. So what do we do? And of course, one option was that sort of protect against the worst case. So do we just say, OK, we're going to build another one, and it's going to be hugely bigger and better, and it's going to cost an awful lot of money? Is that what we do? And they've decided not to do that. It is one of the really good examples of decision making under deep uncertainty. So they've looked at it and said, actually, we think it protects us for now. We're using it more, and we have to use the turbocharged version, but we can do that. What they have is this fantastic scheme of saying, OK, let's keep an eye on sea levels. Let's keep an eye on storminess. And we have a mapped out trajectory of when we start seeing these events occurring, then we need to put in place. We need to be thinking about a new barrier, and we need to put in place extra protection. But we don't necessarily need to do that now. And doing it now might be bad, because we will learn more about what it needs to look like in 10 years' time. But we definitely need to keep a watching brief, because we know it's not going to last. We know we're going to need to do it, but we need to be prepared for designing it at the right stage.
So that's really fascinating. That's what you mean. I was going to make a joke or ask a serious question actually about, in the future, if we've got to be more flexible, should we all plan to live in mobile homes? That when we see there's a flood coming up, move up the mountain. But I think what you're talking about, the flexibility, is basically being aware and ready.
Yeah.
And we talk a lot about flexibility with our clients. Sometimes they say we're flexible, and if you think of a traditional production environment, we're very flexible here. Well, what does that mean? We change things around quickly, and then we work at the weekend. It's like, well, that's not flexible, that's expensive. Flexible is it doesn't cost us any energy to change. And so what you're saying is we need to be ready to do things, but not invest our resources into the wrong things.
Yeah.
I see.
Yeah, I think that's right. And there's another aspect. I don't know if they have this in the Thames barrier, but it's a sort of illustration of what I can imagine happening in flood protection in various places. I can imagine, I'm not an engineer, but I can imagine that in flood protection systems, you can design it for a certain height of protection, a certain level of protection, but you can imagine extending that. So where do you put your money? And one of the things you might want to do is you invest in putting good foundations in for the bigger barrier, but then only build the smaller one. But that means you don't need to tear the whole thing out if it turns out that you're going to need to extend it in the future. You build with that flexibility in the future in mind.
That's really good, because that's a really efficient use of resources, and that's what we're talking about really on the world, is using resources.
It's challenging because it still involves a sort of, it can involve the sort of 10 or 20% more than you need to spend now. Mm-hmm. Getting authorization for that sort of level of spend can be difficult.
So there's a few things we need to go into that are from the book. And I think, one of the things is talking about all the knowledge that we have. The other one's talking about all the computers we have. And then we need to talk about the whole thing about non-linearity. But let's start with the computers, because one of the things that really resonated in the book, and, I've just given you my book as well. It's by way not as scientific robust as yours. It's much more a management story. But how I open the book is talking about electronic speckle pattern interferometry and how that will help you by setting the sails on a sailing boat. And the conclusion is not very much. And we like to say, I'd rather be practically good than theoretically perfect,
right. Yeah.
And you talked a lot about the curse of computers. Now, we're a very digital company, and we do believe in the power of data science and stuff. But tell us, what's the caution point there?
So this had made me a little bit unpopular with some of my colleagues.
Which is a good thing.
I'll take it as a good thing. So the issue there is that we have, over the last sort of 30 years or so, increasingly built models of the climate system. Mm-hmm. And we look to those models to tell us what the future will look like, to tell us how big to build our flood barriers. But they're never quite as reliable as we want. But new computers always come along. Mm-hmm. And the new computers can run a better model. We can see there's you can add more detail. You can do it at higher resolution. Mm-hmm. You can add more processes. And so people go away and do that. Mm-hmm. And my concern is that an awful lot of that effort is done without actually reflecting on what is the problem we're trying to solve. Will a high-resolution, better model be able to solve that problem? If we haven't tied down what the problem is, then simply diving into building a different model and a bigger model will still not answer the question. Okay. And worse than that, it will look as though it does, because models are great at computer models are great at generating lots of data, and we have all sorts of tools to make great images and great videos of what that looks like. And what that tells you is what the future will look like in model world. Mm-hmm. But we're not interested in model world. We shouldn't be interested in model world. Yeah. We're interested in reality. And we have not really addressed how these two relate and when a model will be sufficiently good. So I do have a little bit of a beef that makes me unpopular, because there is, in some elements, because there is an element of the modelling community that is saying what we need is very high resolution models, and we just need to buy bigger computers and run very high resolution models. And I don't believe that's necessarily the way forward, because we haven't defined how high resolution and how complex they need to be to answer our questions. We haven't really fully decided what our questions are.
That's interesting. Now, that's very interesting. But let me maybe take a practical comparison. I love to compare things to other stuff. We'll maybe talk about things like dental health and ecological health later on. But just sticking with this. So I'm going to give a free plug to a mate of mine. It wasn't intended, but Richard Bardwell. He has a company called Shark. Shark like the fish, but with a C at the end. And what his company does is computational fluid dynamics. Posh word, but what it basically means is aerodynamics in a computer. Yeah. So he works a lot, for instance, with Formula One teams, and they have, for the sporting challenge, they have limits how much time they're allowed in a wind tunnel, but he can model the air going over a Formula One car, and they can test lots of different shapes quickly. Yeah. And it saves them, and it's been proven, it saves them a lot of time and a lot of money in building models and testing them in wind tunnels. Yeah. So, brilliant. Can Rich save the planet for us? Where's the difference between what you're talking about and Shark? And I hope you don't mind me mentioning you, Rich. I'm sure you won't.
That is a great question that goes really to the heart of the issue. So, and indeed, that sort of computational fluid dynamics is what I was fascinated by and intrigued by in my early career, because that's exactly what we're talking about in climate. So why is climate different to Formula One design. And you touched on it, actually, because you said it's proven.
Okay.
So the crucial difference is when you're modelling airflows over a Formula One car, you can test it. So you build your model, but you also have your wind tunnel, and you also have out on the track. So you can see, does your model actually match up with your wind tunnel results? Does your model give you design advice that actually allows you to build a faster car? And you can do a cycle. You run your model, you go away, you redesign your car, you run it, you see, was it faster or not? And maybe it wasn't. Maybe you need to refine your model and it gets it better. And you come back and you do it again and you find actually you've got good results.
So when we talk about model there, we of course aren't talking about a clay model in a wind tunnel. It's a mathematical model on a computer.
Absolutely. This is all about computer modelling. Okay. So you've got computer modelling of your car in a wind tunnel, and then you've got the actual wind tunnel. You can test it. With climate, we're talking about predicting what's going to happen in the 2070s, 2080s, 2090s. We're not going to get those results before the model is only of historic interest. So we're trying to find out what's going to happen, but there's no chance of verifying our model. So this is not like your Formula One car, and it's not like weather forecasting where you predict tomorrow's weather, but you do it every day. In fact, you do it several times a day. That's what the big modelling centres do. So you can use your model and you can refine your model and you can tell if your model is any good. More than that, you can tell just how it's failing and you can go away and make it better. It's great. These models, and they're very similar to the climate models, are fantastic tools for weather forecasting, and they're just brilliant. But climate is different because we're trying to predict in a way that there will be no verification because we're 50 years ahead. So you will not have any results to tell whether your model is any good. There's also a second thing. You're predicting what we say is out of sample. You're extrapolating into a different state of affairs. So
we're going to have to slow down and help. I mean, I told you I studied physics, but I wasn't very good. So what does that mean exactly? Extrapolating out of your sample with a different state of affairs.
I got a bit carried away.
Are we on boundary conditions here? Or?
Yeah, we're on boundary conditions. So
not boundary layers for the aerodynamicists.
No. So, but the boundary conditions you're referring to there are essentially the levels of carbon dioxide in the atmosphere. Right. So the amount of heat coming in and out of the atmosphere was moderately stable for millennia, a few millennia. We're changing that. So what that means is we're driving the climate system into a different state. So we don't expect that our observations of the past are going to directly tell us about what it's going to be, how it's going to behave in the future, because we're changing the way the system is behaving. And remember, we have no observations of how it's going to behave in the future. That's not true.
And no reliable data about what it's going to be like.
Yeah. So we're in a pickle.
We're in trouble.
We're a bit in trouble. We know it's changing.
Yeah.
But we have no observations to verify our model with, and we know it's being driven into a different state. There's also a third element here, which is, unlike weather, we've got lots of different parts of the system that have slower timescales. What I mean by that is they change more slowly. So weather changes from day to day, but rainforests change only gradually over a decade or two, ideally over many centuries. These things take a long time, and we have no observations to test it.
I remember that's one of the chapters in the book, isn't it? At the start, like chapter 2 or 3 is kind of the difference between weather changes within a week or two, whether you get a bit more sun or a bit less snow, and actually climate changes, which is the longer thing. It's the short wave and the long wave of climate changes, I guess.
Absolutely.
Could you tell us some more about this? Because I really don't want to go over that too quickly.
I think I've been coming to the end of that. So we have these slow changes, and we're driving the system by putting CO2. So we expect there to be changes for instance, in rainforests, definitely in sea ice, for instance, Arctic sea ice. We're already seeing those changes, but we expect more changes in the future. Changes in ocean circulation patterns, which tend to be fairly slow to change, certainly multiple years, sometimes decades. So we know these changes are going to happen, but we have to build those into our model, and that's a difficult thing to do. But we can't test them because we have no observations of what they're going to be in the future. So it's different to your Formula One.
Yeah, it's the same air as it was last year, more or less. Yeah.
That's right, yeah. And yet I also want to say our models are fantastic tools.
They've got their place.
They really have their place. Because we can't trust our observations, because we're driving it into a new state, we need our models to give us some guidance of what could and couldn't happen. And they do that. They provide us with guidance, really valuable guidance. But we shouldn't think they just give us a prediction. They're not prediction engines, but they're fantastic tools for guidance.
I'm with you. So, I mean, the thing is, we talk a lot about strategy, and strategy many years ago, like in the 80s when I got started, and late 80s, early 90s, working early 90s, well, mid 90s actually. I shouldn't make I was working early 80s, but not in my career yet. But strategy back in the day was a little bit like the old Eastern German 5-year plan. It was like, what are we going to do for the next 20 years? 20-year strategy was quite normal, right? And these days it's not. Nothing to do with climate change, it's just to do with our society. We are a lot more instant and a lot more dynamic. And so we talk with our clients a lot about the difference between a process, a project and strategy. Now, let's not worry about process and project, but they've definitely got something to do with creating something you can sell, whereas strategy these days, we say, is about testing hypotheses. Maybe that's because I studied physics, but strategy is not about saying we'll do this for the next 20 years. It's about saying we assume the market will develop in this way, and that's how we can serve it. Now, I'm not going to plug this company because I don't know if they want to be mentioned, but I had a very fascinating conversation recently. Maybe we can do a podcast with them at some point. And it's a company that makes sensors that help us measure something to do with the environment. And it seems to me that sensors is such an important area to be in, to feed into those mathematical models. If we can actually measure what's happening, then we can keep the models flexible as well, just like building the foundations for your flood barrier.
Absolutely. Sensor technology is so important in this story. And in my career, I've lived through a period when satellite data has become increasingly available. So observations, I'll put it in quotation marks, because what a satellite measures isn't, a satellite doesn't measure surface temperature or rainfall. It measures radiation going out into space. You've got to translate that into what is the weather doing at some point in time. But these are great things that we've got, and we have these tremendous observations of the atmospheric system and the atmospheric circulations. Satellites are brilliant, but they are limited. They are limited even in observations of the atmosphere, and it is appalling, for instance, how land-based observing systems throughout Africa are gradually being degraded and removed. So we're getting fewer observations in really important parts of the world. But the most important response to what you've just said is other parts of the system outside the atmosphere. So in particular, ocean circulation, ocean temperatures, ocean salinity, which controls ocean circulation patterns, and ice sheets, stability of ice sheets. These things, sensors of quite what's happening, are a really crucial element for us to continue to build up better knowledge of both how these systems work and how they might behave in the future. But there is always a but in these things, which is there is a tendency to think if we have better observations, then we automatically know how to use our models. But our models are different to reality. Better observations of reality are really good, but they don't necessarily translating them into how we use our models is a really interesting and problematic issue that does bring in the philosophers
Okay. So that's interesting to get the philosophers, and we're going to talk about all the people coming together in just a minute, but I just need to do a little plug for our podcast series, because we've already done an interview with Spaceport Cornwall, and they talked a lot about the importance of satellites in the climate prediction sector, let's say, the analysis, what's going on. And there's also fascinating things going on this week, talking about looking at subtle changes in the colour of oceans to measure which organisms are there and whether the whales are going to have enough to eat. Just a quick question on the side as well. We live here in Central Europe. Living here on the north-south side, Central Europe. Here in Britain, I live close to Switzerland and Germany. And if you look at the map, nobody else seems to live as far north as we do. And I think that's down to the North Stream, right? If you look at Canada, our kind of, what is it, longitude is the height, isn't it? Yeah. Latitude, sorry. So our latitude, nobody lives here. Will people live here in the next 20, 30 years? Do we know that?
Oh, well, so, yes.
Okay. Right, we'll move on.
Earlier, before we started recording, we talked about how different people have different views of how you might adapt. Mm-hmm. I realised, actually, we weren't talking about that. I was talking about it with somebody else earlier.
Well, that's all right. It sounded fascinating. I said yes. I'm polite.
And we were talking about how the availability of air conditioning has opened up certain regions of the world so that you can live there. So what about us here? I think that in the UK, in Northern Europe, Central Europe, we can be fairly sure that people will still be living here. But your question goes to a really serious point that is a big issue in the world of climate change and climate change research these days. And it relates to this idea of tipping points. And so could elements of the climate system change into a radically different state? And the Amazon rainforest would be one of those. But the big one that we're talking about here is what's called the Atlantic Meridional Overturning Circulation, AMOC.
That was the one I was thinking of.
And this AMOC is a really groovy, exciting sort of physical thing. So it essentially represents a flow of, it's part of the what known as the overturning circulation in the oceans more generally, where water flows essentially relatively close to the surface from the equator towards the poles in the Atlantic. And when it meets the cold water from the Arctic Ocean, it sinks and then goes back south in the depth. But the point is that this carries a lot of heat up to the North Atlantic, and it's part of the process that keeps Northern Europe warmer than it would otherwise be.
Right.
So your point about this is why this is a particularly populated area, because we have a particularly benign climate for the latitude that we're at. Now the question then is, could it be that circulation pattern could shut off? It's known as AMOC collapse.
Right.
And it's known as tipping point in the system.
Oh, so the tipping point is where it collapses.
Yeah. So could that happen? And there's a lot of debate about that. There's suggestions that this, in the paleo record of observations of tens or hundreds of thousands of years in the past, that suggests this has happened in the past. There's also mathematical understanding that says, yes, this circulation has both an on state and an off state. So this is possible. But could it happen in the next 100 years or 200 years? Well, some people think it could. Some people think it couldn't. Some people have made predictions that it could happen in the next 20 years. Other people say, actually, no, we don't know about that. It could happen at some point, but it could happen. We have no knowledge about just when it would happen. So this is really an active area of research, but tying down what we know and what we don't know about AMOC collapse, not just about the probability of collapse, but what it would mean for Northern Europe and for other places in the world, is a big area of research that we're involved in here at LSE.
All right. Well, I'm definitely going to be buying a mobile home in that case then. But let's then move on to non-linearity and then talk about the solution with people afterwards. But I think this is a point, and this is, if you read this book, and I really would recommend everyone to read this, if you've got just a slight interest in facts, it's worth reading. It's worth, and even if you don't read the whole thing, if you're not very scientific and it's a little bit deep sometimes, read as much as you can, because I find it absolutely fascinating, and it's written, by the way, in such a great way that it is accessible. You've got a brilliant skill to talk about complex problems in a way that people understand, and we've
really appreciate that.
No, but
it's difficult to know. When I started writing the book, I had sufficient arrogance to think, yeah, I know what I want to say, and I can write that so that anybody could understand it. 7 years later, I realised that at the start I didn't know quite what I wanted to say. It took a lot of work, and writing it so that it even was potentially understandable was a lot harder than I thought. But thank you so much. That it seems to work for you is great.
Well, it certainly did. And one of the things, one of the hardest things to create a mathematical model to talk about is something that you had such a great image for, and that was the non-linearity. Now, we've just spoken about some people think it will, some people think it won't. For the average CEO out there that doesn't know a lot about science, you would like to say, oh my word, when are they going to make their minds up? All these scientists arguing with each other, and they've all got these opinions. Now, don't get me wrong, politicians seem to be arguing with each other and have opinions. The difference is they're not fact-based. Now, when we get to a scientist, these are people who spend a lot of their life thinking about things in detail, testing things, getting the facts together, going to conferences, speaking to each other. Why can't you make your mind up? And this is me leading you towards non-linearity, because I'm sure there are lots of answers to that question. Why can't scientists make their mind up? But let's stick with the non-linearity side.
Yeah, so there are lots of elements to that, but we'll stick with non-linearity. But before I talk specifically about non-linearity, can I just make some comment about the uncertainty?
Yeah.
So uncertainty and confidence are two sides of very much the same coin. Mm-hmm. So and this is where you get the what we know and what we don't know coming out. So for instance, you can know the increase in greenhouse gases in the atmosphere will trap heat in the system that will almost certainly lead to increasing temperatures.
Okay.
And there are other aspects of that.
And that's something we can measure as well.
And that's something we can measure.
So shark and aerodynamics.
Absolutely.
We predict it, we measure it,
we measure it, it happens.
Okay.
It's really known. And we know that it will continue to happen because we know why it's happening. Mm-hmm. And other things as well. It's sort of not just temperatures go up, but that land temperatures will go up faster than ocean
ice
temperatures.
Ice starts melting. Yeah, there's a big ice block on its way to hit an island at the moment. We've heard about very big ice.
South Georgia, isn't it?
Yeah,
that's
South
right,
Georgia, yeah.
Yeah, that's right. Yeah.
Let's keep the fingers crossed by the time this podcast comes out that
it doesn't get redirected slightly. Absolutely, yeah. So there are some things we know. So, but if you come back to just temperature increases, you can say we know that on average temperatures are going to increase. You know that even on almost any area of the world, that temperatures are already increasing and that they're going to continue increasing. Fine. At the same time, how much are they going to increase by 2100? Actually, that's really uncertain for all sorts of interesting things about feedbacks in the climate system, what's going to happen to clouds, what's going to happen to the gradient of temperatures in the atmosphere, all sorts of really cool physicsy things tell us that we're hugely uncertain about how much change we'll see. But actually, that we will see changes that are significant for the societies in which we live, we're very, very confident about. So you have a sort of confidence on one thing and yet really uncertain about just how big it could be, about the scale of change that you could see. Now, why is the uncertainty there? It's for many, many reasons. There's philosophical questions, there's issues of models, but the non-linearity is where it gets really interesting, because sometimes there are some things that you just can't predict accurately beyond a certain period ahead. So that's the case in weather forecasting. It's non-linearity in the system that means we can't predict more than 10, 15 days ahead. In practice, weather forecasting systems are pretty good for up to 5 days, usually, sometimes more than that. But there's a theoretical limit that will say, you just can't do reliable weather forecasts out beyond about 15 days. Because
it's true, all the apps, even if you get the pro version of the app, it goes to 14 days, doesn't it?
It's not going to go
beyond that.
Let's face it,
anyone who's been skiing knows, we'll look on the evening before whether we should get up early and get on the first
And
lift.
it's reliable.
Yeah.
And it's reliable the evening before.
Yeah.
But if you want to decide whether you should book your holiday 3 weeks in advance, no, it's not.
Yeah.
It's just not. And that's because of non-linearity. So what I mean by that is, what do I mean by that? It means interacting processes. That's kind of complexity rather than non-linearity. It's kind of like throwing a dice. So when you throw a dice, you don't know what number's going to come up.
Right.
And you can't throw it again and again, getting the same answer, because the details of just how you throw it affect what's going to happen.
Right. Okay.
And if you want, I could talk about double pendulums, because you mentioned
what
those.
I would love to know about.
So,
I'm going to set our team a task of animating a double pendulum. You're in trouble, folks. But anyway, I'm sure somebody must have done this on YouTube already. Let's see if we can build our own.
There must be one, yeah.
Okay. What's a double pendulum then?
The double pendulum is just this beautiful illustration of how you can understand what's going on. You can understand the physics. You know what's happening, but you still can't predict exactly what's going to happen. So if you imagine a pendulum, a normal pendulum, you set it swinging, and it swings at a certain frequency.
Oscillation,
and it's entirely predictable, or it's very reliably predictable. If you go to the mathematicians, it's actually quite complicated in its detail.
Okay.
But we're physicists, so let's not worry about the mathematicians.
No.
As physicists, you make a little approximation and you can predict exactly what it's going to do. So predictable, it's used to measure time. It's been used to measure time.
That's how predictable it is.
That's how predictable it is.
And to be fair, a teacher of mine at school said that physics is just maths with pictures.
That's probably true, but it's better than maths. That's going to cause me trouble.
Oh, we're going to get the maths trolls out now. We didn't mean it,
No, it didn't mean it,
We
honestly.
love you too. Anyway.
So now, if you imagine a pendulum. But now, I'd stick another pendulum on the bottom of this one. So you've got two pendulums.
Pendulum hanging off a pendulum.
A pendulum hanging off a pendulum. Now, the thing about this is, this as this is sort of your basic physics. This is just Newtonian mechanics here. And Newtonian gravity. So you've got gravity.
An acceleration.
And you've got acceleration.
Potential energy, kinetic energy. It's like a kid on a swing, right? We've
all
been on a swing as a child. If you don't understand physics, get on a swing. You stop. You always stop at the same point on either direction, the front and the back, unless you swing your legs.
Absolutely. And if you've got two swings, you've got your kid next to you on one swing and you on another swing. You're a lot heavier, but actually you'll swing at the same rate.
Exactly, because the earth is accelerating you down, and it's easier to get a child high in the air than it is a heavier person. but also the heavier person is going to get down quicker again.
Well, the frequency that which you oscillate is governed by the length of the pendulum.
Okay.
So you're sorted, but you've got...
Sorry, just a fun fact for anyone who doesn't believe this. Have a look at an old clock with a pendulum on it, and you'll find that there'll be a thread where you can actually move the pendulum up and down or something similar. Because that's changing the speed, basically, isn't it?
Yeah, absolutely. So that's cool. It's very predictable. Put one on top of the other and set them going, and it just behaves in a really wacky manner.
Okay.
And the point about if it's single pendulum, if you set single pendulums of which are the same going at the same time, they will stay in tune and then very gradually, due to friction, move out of tune. But there's a predictability there. If you've got a double pendulum, you'll get the animation. It does really wacky things and is not predictable beyond a second or two. It's very difficult to predict. Because of the non-linearity.
So just to make absolutely certain that nobody tries this at home, we are not suggesting that you take your child and ask them to hang off your legs whilst you're on the swings. It will have a very chaotic result, but it's a different thing to non-linearity, right?
That had not even occurred to me.
Okay, so don't
But
do
it
this at
isn't
home,
advised,
folks.
it's true.
Yeah, we'll stay away
Although
with
it
that.
does sound fun. No, it's not advised.
No.
It's not advised.
Okay. Well, listen, let's start talking about the solution then, because we talked about the problem. We talked about, what issue do we have? Why should we care about it? Well, let's face it, we need to know whether to build a Thames barrier or a new Thames barrier or just the foundations. And we talked about the necessity for flexibility, which is basically let's build part of it and then build the rest when we know how much. Yeah. Another fun fact, if you go to the Terracotta Army in China, which I would advise everyone to do if you can get there sustainably, it was on my bucket list, an amazing experience. Now, they have many areas that they haven't uncovered yet. And the reason is because the Chinese are very clever in so much as they've said, we don't have the technology to do it properly yet. So they've only opened up not even a quarter of the army. And they're not putting these terracotta soldiers into the atmosphere just yet because they lose their colour very quickly. And they've got some technologies to avoid that, but not good enough yet. I think that's an excellent philosophy and an excellent culture.
It's a beautiful example of humility in terms of what we know, and that acceptance that we will know more in the future. But it shouldn't stop us doing stuff now. So they've got dug some out, which is fantastic.
Yeah.
But caution to say, actually, we might be able to do this better in the future.
And I think making big conclusions about the environment now is probably bad as well. We should base the facts on what we know, stick with the linearity, if you like, and then, as you say, keep flexible for the non-linear stuff. So it's like, okay, let's get ready and be active and aware so that we know when to make which decision based on the facts that become more reliable, the probability that becomes closer to 1 instead of 0.1, 100% certainty.
That's absolutely right. Although shifting a little bit into, I think, your world and what you would be more knowledge about than I would, there's also a judgment to be made in terms of whether it's sensible to wait or whether that involves extra risk that actually you need to protect things now. So there's a judgment of when you decide we know enough and this just has to be done now.
Do you know, you just reminded me of something. I'm interrupting you, and I'm sorry, David. But okay. When I get motivated, I have to get things out. One of my greatest strengths is not being quiet. And I've forgotten her surname. I think it began with P, and I interviewed a very fascinating lady about 10 years ago called Karen. It wasn't far away from where we are here at LSE. And she had an absolutely fascinating job. Back in the day, I used to do written interviews for the Pocket Progress Coach. It was a great thing we did back in the day. And she was responsible for a company who was a non-profit, I believe. At least they were sponsored by all the oil companies around the world. And they weren't there to give advice, but if there was an oil disaster. So, for instance, she talked about a T-bone. And T-bone is when one oil tanker sails into the other one. Okay. And so you've got two boats full of oil that have hit each other. And so her job with her team was to go out to these natural disasters or to these man-made disasters where there was an oil spill, whatever, and to give scientific information but not advice because of liabilities and things. But to the country that was going to suffer, their job was they were basically sponsored by the oil industry to say, we'll send our specialists. You can ask them anything. They'll tell you, and I think on a practical level they probably did give advice, but officially they didn't. Right. Now, she said an absolutely mind or game-changing phrase to me, which has stuck with me for the last 10 years. And she said, Nick, you don't have to just measure the risk of doing something. You also have to understand the risk of not doing something. So if you imagine these two oil tankers, going backwards could create a spark and it could make them both explode. But leaving them stuck in each other in the ocean is just as likely as making a spark, or maybe likelier. Yeah. So the risk of not doing anything, and I think that's what you're talking about. We don't know. We can't predict the future. It's even in the title of your book. We won't know everything. But it's not just the risk of getting it wrong, it's the risk of not doing anything at all.
Absolutely. And yes, I couldn't agree more. It is really important that we act and build up resilience across our societies, because this will take decades longer to do.
Yeah.
So we do need to start. But as I said earlier, there's advantage in building in flexibility to change it and extend it during
So it's
the
not
future.
about doing nothing, it's about doing the right thing in the right way.
Yeah, absolutely. Yeah.
Well, let's move on to that then, and then we can wrap this one up, because this is really fantastic, But what's the solution? I think we've offended all the mathematicians, but should we invite them back to the table? The book talks as well a lot about the various disciplines of science.
Yeah, absolutely. So the mathematicians absolutely should be at the table. But there should be an awful lot of people at the table. So I'm essentially a climate modeller, or by background. I spent a chunk of my career doing climate modelling. So I kind of see that as a centre piece. I think the models are important, but we need to expand from the climate modelers. We need the mathematicians, and we need the philosophers on board. We need the impact scientists, so that might be marine scientists or agricultural scientists. We need the engineers. We need the impact assessors, and we need the civil servants, politicians, and we need business, and we need the economists. So why do we need all these? So starting from the modelling, and there's no reason why you necessarily should, but that's where I come from.
Yeah.
You need your mathematicians and your philosophers to question the robustness of what you're getting from your models, to say, okay, but where are the foundations of this? Sort of think about mathematical systems, chaotic system, non-linear systems, and say, what would be predictable in such a system as that? To bring a different dimension to our interpretation of the models. But then also, you want the economists and the business planners to be in the room and say, well, okay, you're talking about robustness, but robustness of what? What should you be trying to do? What sort of information should you be trying to get that we can use? And at the moment we have, this is going to go back into whinging a little bit, but at the moment we have the sort of concept that the modelers in many ways work independently. And while nobody would say they're doing this, there's a sort of subtext of, well, we're trying to make as close to a perfect a model as we can, so we can predict everything.
Because that's my silo. That's what I do.
Yeah.
I'm the modeler.
And the modeler.
And let's let somebody else worry about the rest. Yeah.
Yeah. So we do the modelling.
Yeah.
We then give it to you, adaptation people, business, to the economists, who will then use it.
Yeah.
I would argue that where the philosophers and the mathematicians come into the room would say, that's not going to work. You're not going to get that. So we need to be a little bit clever about how we use our models, how we use our physical understanding to say what could happen.
Yeah.
And that brings in something quite interesting. It says, if you're not going to get a reliable prediction of everything, what you need to do is choose what you're going to focus on, because what you're going to do is provide information, but it's going to be better about some things than others. So what is it that you're interested in? Now, as a physicist, I understand why the modelers and climate scientists often focus on something like global mean temperature. There's good physical reasons for that. It has less uncertainty, so it's great. But if you're building a new reservoir, or you're building a flood protection system, global mean temperature isn't going to be much use to you.
So that's the bit where we have to get the civil engineers, and then we need to get the hydrologists, and we need to get the meteorologists, and the physical modelling specialists, and also the local politicians, and the investor, and the person who's going to build a factory on the top of the mountain or whatever, to all come together and say, okay, this is what we need to work together to reduce the probability of failure.
That's right. But crucially, most of those people who are active in building a better, more resilient world, which is great, there's a tendency for them to get information just directly from the models, not to talk to the modelers. I mean, this comes back to the dangers of computing, that sort of given the wonderful facilities we have today with the internet and with the advent of AI in many areas, there's an opportunity to make the data from the model easily available. But that's a problem, because that creates the separation. So you've got all those the structural engineers and the like don't need to talk to the modelers, don't need to talk to the mathematicians or the philosophers, because they can just go and get the data. And the data then gets misinterpreted as a prediction. So they need to be actually in the same room. And understanding, well, what assumptions went into that. So the model says this, but is that reliable? Do you think that's reliable? And I've got into, so if I may, if we've still got time. So things like, I've been involved in exploring model uncertainty. All the models that we had in our experiment that was exploring model uncertainty, and there were thousands of them, all of them showed an increase in winter rainfall in Northern Europe. So should we trust that? Well, the fact that all of them did possibly is a valuable piece of information. But actually, if you take that piece of information and go away and think about it as a physicist, you would say, well, actually, our weather systems in winter come from the west. And they do that because of the direction that the Earth turns. The Earth isn't going to stop turning in that direction. So our weather systems in winter are going to be coming from the west.
The warm, wet, whistly winds.
The warm, wet, whistly winds. Absolutely. And crucially, they are wet because there's an ocean there. And whatever happens with climate change, there's still going to be an ocean there. But with climate change, the atmosphere is going to be warmer. It's going to hold more moisture. So, first order expectation is, in winter, it's going to get wetter. So we have models telling us something, but we also have a physical understanding that that's likely to be the case.
I understand.
So there's something robust there. So I talked a lot about uncertainty, but there's something where you get in the room and say, should we be building for wetter winters? Actually I would. But I wouldn't. Models tend to say drier summers, but actually I'm not sure I would put anywhere near as much confidence on that, because we don't have a physical explanation. And when you start to push the models to see if they'll do other things, actually you can get different results there.
So if you go to the maximum tolerances of the models, then you can actually stress test the assumptions. And I see it. So I mean, there's just to make a sort of a practical comparison to this. If you're looking at production environments and you want to improve their reliability of delivering parts on time, we need to look at which parts come from the suppliers on time and which stations in a production line. If you think about Henry Ford, a line of production where cars are being built, and if you say, okay, well, each station on the production line has an 80% reliability. I think most companies would be very upset with that, but I know some that would be quite happy getting to that. But if every station has an 80% reliability, well, it's a chain. So you've got 80 times 80 times 80. If you imagine about the parts arriving on time, let's call it something like that. If we've got 3 or 4 suppliers and they need to supply parts on time and they've got 80% efficiency, reliability. Of course, if you've got 2 suppliers with 8% reliability, it doesn't mean that the system has 80% reliability. It's got 80% of 80%, which I believe is 64%. And then you got the third supplier, then we're down to, what is it, 56%? Please, I can't do this in my head. Physicists, no, not on camera. I tell you. Anyway, but you get the idea. It's the multiplications of things going wrong. It's not that everyone has the same, it's the multiplication.
It is. And this is a really crucial aspect of climate change, which I come to towards the end of the book. So I mean, as you said, I start with these sort of how it all connects, and hopefully that's fairly easily understandable. Then you get into the non-linearity stuff, which is really interesting. But then I come out of that into the economics and how we respond. And one of the things that I touch on in my book, but have also been moving into since writing my book, is this idea that with climate change you might expect an increase in extreme events and disasters associated with this. And so we see on news screens this idea of floods or droughts, wildfires, and there's a tendency to think that's what climate change is that you might get hit by that. That's why you might want to avoid it. And I think that's a good argument. Yeah. I would completely buy that. That's true.
Thing, that's
absolutely
worth taking
true.
seriously.
Worth taking seriously. But I also think that quite a lot of people might look at that and think, yeah, but I live halfway up a hillside. I don't think I'm going to be flooded. I don't want other people to be flooded, but I don't think it's that.
It's not my problem.
It's not, and similar with drought. Surely we can just build more reservoirs. It's going to be okay, isn't it? And what this misses is two things. But to direct to your question, in your supply chain, you might have quite a lot of different potential sources of crucial elements that are distributed around the world, or around a particular nation. But the chances that one of them gets hit in any year is going to increase. Now, it doesn't mean it's likely, but it's going to increase. And if it gets hit, then your whole chain collapses somewhat and you get losses in that. And maybe the prices of these products go up to account for the increasing risk. And the chances of 2 or 3 parts of the chain getting hit, not necessarily in the same year, but over 2 or 3 years, that keeps knocking your system, has increased very substantially. Again, it doesn't mean that it is likely, but the likelihood of a sort of 1 in 200 event happening has gone up. The likelihood of 3 of them happening over a period of years has gone up even more. And so your system becomes less stable.
So that's basically the opposite of whether the parts are there on time. It's about whether the unexpected event happens.
Yeah.
I see. So this is really great. And I think we've heard so much today which really starts bringing the facts on the table. And the great thing about having the facts on the table is people can start doing something with it. And we've spoken about people come together. And I'd like to invite you to join the Earth Circle. That's our new movement, which is all about people coming together. And we want to promote this more and more this year. And you're really, as the Germans would say, you're speaking from my soul. You're walking into an open door.
Fantastic.
So I think we need to get more and more people to start collaborating, to bring their knowledge to the table, to reduce the uncertainty, take the guesswork.
Their skills. Yes.
Take the guesswork out, right?
Yeah, absolutely. Yes. Yeah.
We say that sometimes about our company. It's about take the guesswork out of progress. And if we talk about artificial intelligence, we've actually got our own artificial intelligence tool. And we've got a whole big catalogue of progress factors. That's the name of the company. And so we work with, for instance, boards of directors, leaders of a change, something that a company wants to change. And we get them together. We do a North Star workshop, and the software helps us out of our many, many progress factors to find the 10 that are right for those people. Now, you could say, why have we just invested a lot of money in updating this whole part of the software? ChatGPT can do this quicker. We spend a half a day or a whole day, depending on the client, actually deciding what are the 10 factors. For instance, daring to take a risk, sharing what we've learned, looking after our mental health, involving scope 3 suppliers in environmental things. There's all sorts of stuff. There's data-driven decisions. But there's, a lot of human factor sides there as well about going to compromise. And we could just put these into ChatGPT and say, what are the 10 things my company should do? We're a large business and we want to do this. And we thought about it. We thought about just using ChatGPT. But the point is it stops people thinking. And then people rely on the computer as the be-all and end-all. And we've all seen with some very famous examples of like when Google launched its AI tool and it got things wrong, or I think Mark Zuckerberg was described as a very dangerous man. I'll leave it up to the audience to decide whether that was a good or a bad prediction. Maybe time will tell. But the thing is, basically, we all know that AI isn't reliable, not 100% reliable. It's a tool that we can use. And there are many of these tools, and there's many brains out there, but nobody knows everything. And I think what I'm taking away from your book is we all need to get together, join the Earth Circle, start working together to reduce the risk of fail, to take the guesswork out of progress.
We do, absolutely. I mean, I couldn't agree more. Yes, it's a very exciting initiative. Yeah. I'm really enthusiastic. So usually I've got lots and lots and lots of things to say. So, but here is sort of just a sort of yes, absolutely. That's great.
Well, I mean, that's an absolutely perfect way to bring a podcast to an end. We've talked about the problem and why we should care about it. We've talked about why the problem's there and why we can't fix it. And we talked about what we can do to deal with it. We can't take away the lack of predictability, not today at least, but we can deal with it and we can reduce the effects of climate change. And
we can, and something we spoke about a little bit before we started recording was building, this idea of building the future. And I think this goes to your point about AI. AI, when I'm asked about AI, is always difficult because it's a hugely powerful tool for some things. But your point here, and I think it's right, is we've got lots of human expertise in lots of different areas, and we're trying to work out our way forward. And what I think we should be aiming for is aiming to build a future that we want. Now, of course, everybody wants a slightly different future, so we're going to disagree, and that's fine, but we should be thinking about what sort of future do we want, how do we build it? And that's about bringing people together, different expertise. How do we go about that? What's going to achieve what we want?
Well, I mean, it's wonderful that you and I have found each other this week. Not only do we have a similar surname, but I think we have a very, very similar approach and philosophy. But just like if you imagine looking at for instance, this microphone that's here on the table, I'm looking at it from one angle, you're looking at it from a different angle. We see a different object, even though we've got the same approach. And I think that's what it's all about. And I really want to thank you for finding the time today. It's been absolutely excellent.
Thank you so much for reaching out. I've really enjoyed our conversation.
All right. Don't forget to buy this book, folks. For those that aren't watching this on YouTube, Predicting Our Climate Future by Professor David Stainforth. Stainforth. That was hard for me to say. I just spelt my own name wrong and your name right. That was difficult. I'm proud of that. Thank you, David.
Thank you very much.
Excellent. Okay. Thank you so much. Wow. I just so enjoyed that conversation. I've said many times before, I'm not the best physicist in the world, but I'm fascinated by physics. And hearing physics in a way that it's related to real world events is so important and so interesting. What I loved about listening to David Stainforth was to hear his realistic approach on the world. When I was reading his books, one of the things that really hooked me was when he said, hey, we're getting stronger and better computers that can model all sorts of systems. But are we actually asking ourselves whether we need those computer models? He's such a great practical guy with such a wealth of knowledge. And I do hope that you enjoyed that podcast. If you haven't subscribed to our channels yet, please do that. Please subscribe wherever you're streaming this podcast. Please go to YouTube, subscribe there as well. It does make a difference to us how many subscribers we have. And the same thing again, we're on Instagram, we're on LinkedIn, we got a website, we're a very chatty organization. Follow us wherever you can. It really supports us, but also get in contact, send us a message. I've had some wonderful conversations with people who have watched our YouTube films already. I'd love to hear from you. Tell me what sort of podcast you'd like to hear. Tell me what you like the most about this podcast. Tell me what you think we should change next time. The team and I are so thankful for all the feedback we're getting and all the interaction with our slowly growing community. Thank you so much. Bye-bye.